Okay, we're gonna get started here again, and so just to finish out, I'm gonna let Paul talk about this, but Paul had just thought that was a great presentation, and he had some stuff to add on to it. So we're gonna get a supplemental presentation that is not in your book, so don't be looking for it. So this is additional information. You're getting your money's worth now. But we'll do that, and then we'll jump to the schedule and get back on schedule and all that. So it'll all work out. We'll be fine. We're ahead of schedule anyway. And then also after this presentation is all done, we will bring all our presenters up, and then we're just going to put them under fire, and you guys get to ask your questions. So, and we'll be watching the virtual presentation, or excuse me, the virtual webinar for questions and bringing those forward. And at that time with the Q&A, we'll try and do as best we can and getting the mic around to people so the virtual can hear it really well. But anyway, I'll turn it over to you, Paul.
Great. Yeah, watch. I thought the Chris's presentation was just outstanding, and it reminded me of something I thought would dovetail very well with it, so that I hope it does. Please take me to task on anything that doesn't. And that's talking about water infiltration to the soil and why it does things like why a tile drain, for example, doesn't dry out your field. So there are two forces that make water move through the soil. One is capillary action and the other is gravity. Capillary action is a combination itself of two things, adhesion and cohesion. Cohesion is the attraction of water to itself. Adhesion is the attraction of water to something else, like adhesive tape. So if I put my finger in a cup of water and hold it up, we've got adhesion holding the water to my finger and cohesion holding water droplets to other water droplets. So of these two forces, capillary action and gravity, which one of them is stronger? It depends. You know the answer to every question I give the audience. It depends. It depends on what? How much water is in your soil? So if my hand is the soil and I get it wet, now it's saturated. There's no air around my hand. Now you can see gravity pulling water off of my hand. Gravity is stronger than capillary action. Okay, at this point now, you can see the water droplets holding onto my fingers. At this point, the capillary action of my fingers is equal to the strength of gravity. My hand is now at field capacity. That is actually the definition of field capacity. It's the amount of water that your soil can hold against the force of gravity. When your soil is wetter than that, gravity dominates. When it's drier than that, capillary action dominates. So field capacity is that point where the switchover occurs. So we already talked about the different sizes of the particles. The more surface area you have, the more capillary action per volume you have. Therefore, sand has quite low capillary action and clay has very high capillary action because of the sizes of the different particles that we were talking about before. These are probably some of the oldest slides you're going to see. I found these actually in my dad's cabinets in the big warehouse part. These were slides, as in Kodak carousel slides, that I had converted over to PowerPoint slides from work done in the 1950s at Washington State University. Fortunately, soils and water are exactly the same now as they were in the 1950s, so they still work very well. In this case, what they did is they have soil of different textures and different water contents that are squished in between plexiglass so you can see how far the water goes down. In this particular example, they've got loam, a sandy soil, and a clayey soil that they've put water on for the same length of time. Notice that the water went deeper in the sandy soil than the loam, and much deeper in the loam than in the clay soil. Why? Well, the answer is sand has bigger pipes. Water moves faster through bigger pipes. So even though clay has more air space, it's got higher porosity, the pipes in the sand are bigger, so the water moves deeper faster. This looks the same, but it's not. This is the same amount of water was applied to each of the three soils, and we let it go down as deep as it was going to go. Notice in this case, the water went farther in the sandy soil than the loam, and farther in the loam than in the clay. Why? Well, in this case, the water holding capacity of the sandy soil was less than the loam, and therefore it took more soil to hold the same amount of water. So it looks really similar to the time frame one, but the rationale is a little bit different. In this one, we've got a loam soil that's been squished in between, and there is some cotton right here, and the water was literally introduced in the side. The soil was originally dry before they put the water in. So here's a good visual representation of which is stronger, capillary action versus gravity. Since the soil was dry, capillary action was stronger, and you can see that it's pulled the wetting front up against the force of gravity. Now, if you notice, it did go farther down than up. Gravity plus capillary action did have some effect, but that extra difference was quite small compared to what the capillary action was doing. Therefore, if you have salts in here and the water is moving upwards, it'll carry the salts with it. In fact, I jumped ahead just a little bit. This is the exact same experiment, except in this case, they put little spots of water-soluble dye. Now, this would represent a mobile nutrient like nitrate nitrogen, for example, but it also represents the way salts would move in our leaching operation. If the water is being put here, notice that as it moves up because of capillary action, which direction the salts or the nutrients are going. Notice in no case does the salt move upstream from the water. It moves along with the water, and it also spreads out due to diffusion. So we've got mass flow and we've got diffusion as it spreads out, but nothing swims upstream. Okay, so now we've got a notch in the soil. So this would be kind of like a furrow irrigated field that you've taken a cross section of. They've got a flask or a beaker filled with water that's filling up the water in that notch. And you can see the wetting front and how it moves like this. This is a layer of sand then underneath it. What's going to happen to that water as soon as it hits the sand? Shouldn't water go down through the sand? What's going on here? This is a loam soil, this is a sand, and for some reason, the water didn't penetrate the sand, it just spread out. Okay, which has more capillary action, loam or sand? Loam, more surface area, which means that right here where the sand and the loam are touching each other, they're both fighting for the water, and the loam has much better attraction than the sand does. It's pulling the water harder. Therefore, the water is moving laterally and sideways rather than going down into the sand. So this means a layer of sand will inhibit water infiltration, right? No. What happens when the soil right here becomes saturated? Which becomes more important in a saturated soil, gravity or capillary action? Gravity. As soon as the soil becomes saturated right here, gravity takes over and it pulls the extra water out. So this is an outstanding situation for us to have for a crop, because this soil will be at its field capacity and will be holding all the water that it can hold. But if it ever gets to the saturated point, then the water flows out down to here. So this stays at field capacity. This is what's called a well-drained soil. Maybe it's well-drained because there's a drain pipe in it. Maybe it's well-drained just because we've got sand or gravel layer deeper and the water table is down 150 feet, like it is where I grew up. We don't have these shallow water tables. It's very, very deep. So this is ideal. And when they're building, say, a putting green for a golf course, they commonly put a layer of sand, and then they put a layer of a loam on top of it, and then they plant the grass on that. That loam layer may only be an inch or two because they irrigate it every night. But that's what they're looking for, a finer textured soil to hold the water and then good drainage down underneath it. Let's say instead of that sand under here, we've got a layer of clay. So this is loam, then clay, then loam. We've got that same wetting front moving out that's about to hit the clay. What's going to happen when it hits the clay? Gosh, the clay's kind of absorbing water. Which has more capillary action, clay or loam? Clay. So you can see this kind of little eyeball poking out here. The clay is actually sucking water out of the loam because it's got more capillary action. So that means a clay layer is good for water penetration. No. What happens if we give it a little bit more time? Now we've got this spreading out, but it's a very different source of spreading out than this. In this case, what's happening is the water is moving down relatively quickly in the big pipes. It's hitting the tiny little pipes of the clay, and it's spreading out because there's no place for it to go. What is the water status of the soil right here? Saturated. This is the saturated soil, no oxygen that kills the roots and ruins your growth. This would be a great example of what if we put our tile drain pipe right here? Well, as Chris was saying, you're not going to drain the soil because the soil is saturated here. Your tile drain is down here where it's dry. In this situation, we need to either break up that clay layer or have the tile drain pipe right here. Questions or comments on that? Yes.
So I read as well that depending on.
Okay, I thought I was yelling. I also read that when water changes, so we're dealing with gravity, water going downhill, and it hits a dissimilar substrate, it causes an anaerobic flush, which causes more weed pressure as well. Do you biologically see that as an issue?
I don't follow the last connection, the anaerobic conditions giving you more weed pressure. I guess I could in the sense that in an anaerobic condition, your crops are not going to grow, and something like foxtail or ladyfinger. Do you guys have ladyfinger up here? And ladyfinger will grow. You can always tell where the swampy areas are in the fields I work on, because there's a certain weed called ladyfinger that only grows in anaerobic conditions. So anywhere you see it, we know that's anaerobic.
So the second question is a hornet's nest, I guess. Do we have a third condition called anti-gravity in, so first, water is lazy, it goes downhill. So we're dealing with capillary or gravity for it going down. But when we only have 10% humidity, a hot wind, and the top 16 inches of the soil is saturated, in fact, we're losing a lot of moisture to anti-gravity into the atmosphere, which I'm saying really goes into Chris's and what I'm trying to advocate what you're saying, break up those layers and drain it to get the salt down, because otherwise we end up with what's called a sodium seep. And so as moisture is anti-gravity going into the dry atmosphere, it's leaving dissolved solids at the surface. And that's integral to our desert irrigated farming. I think anti-gravity capillary action, making a toxic top inch of the soil, is really important to how we irrigate and get those salts out before they end up a sodium seep.
I certainly would use the phrase capillary action rather than anti-gravity, but absolutely, you've got the capillary action of the soil that's bringing the water up. You've got salts that are moving up with the water. If you've got plant roots here, they will take up some of the water which is lost due to transpiration about the leaves, but they will leave the salt behind. If you don't have that, then this will go to the soil surface, your water evaporates, and the salt is just left right here. And in fact, if you fly over southern Idaho, northern Utah, it'll look like somebody's played a war game with hexes on the desert, because you'll have these hexagonal shapes where that salt comes to the top and then the last spot to dry comes together. And the vegetation will follow the hexagonal shape. So it will literally look like hexagon filling up the entire desert, specifically because of what you're talking about. So the fix is, among other things, lower the water table. You need the water table deep enough so that capillary action cannot pull your source of water continuously up. In general, that's 5 feet-ish or so to stop the what you're talking about. 5 foot depth of water table. Yes, where that water table is sitting between their irrigations, it depends on your soil texture, but you need it something like 5 feet or deeper in order to prevent this continuous upward movement of water and then salts.
That slide you just have pulled up with the dye, there's that row of dots that are virtually horizontal.
Yes.
Why is the dye going slightly uphill, but the water arguably went further down to the bottom of the chart?
I have not noticed that before. That's a good question. I would say They probably didn't do a perfect job of where they injected the water. I bet the water seeped down about here. So the center point of water injection was probably more like here than here. But no one has ever or I have never noticed that angle of the dye before. So that's very interesting. All right, up to this one then. So here we've got a situation with the furrow on top and a hole on top. And notice that as the water hits here, it runs down the hole and then it gets into the soil and seeps out sideways. Notice how the penetration is better here than it is here directly underneath where the furrow is. So that pore, this macro pore, improved water penetration. Why did it not improve water penetration right here? How much capillary action does air have? None. There was nothing to pull the water into this big empty area here. Why did the water go in right here? Because it's saturated right there. What happens hypothetically if the soil becomes saturated right here? Then gravity takes over and now it pours it into the hole and now it drains down the hole. That's how a tile drain works. A tile drain removes none of the water from your soil unless the soil is above field capacity at that location. So you can have all the drains in the soil you want. It will not lower your soil level below field capacity. It won't dry out your soil because of that. Here is something that was a really big deal in the 50s, became completely unimportant in the 80s, and is now kind of becoming a big deal again. And that's the idea of vertical mulching. The idea was that, hey, we can put a layer of straw like this, then water will hit the straw and it'll improve the water penetration. You notice how much deeper the water went here than it did right here. What was the problem? Well, and they actually had big machines that did that. You work it in the ground and you'd put a layer of straw to the ground. The problem with it is if this is broken on top, if you just get soil moving around on top due to wind or mechanical or anything else, now you have this isolated bit of straw in the soil, and you notice that this does not improve water penetration at all, or at least it wouldn't until the soil gets saturated right here at this point. So there was this original idea that vertical mulching was going to be the wave of the future, and it never caught on, except now this is one of the advantages of strip till, if we're talking about strip tilling. We end up with a situation where we have crop residues that do go up to the soil surface. And so a strip tilled soil gets better water infiltration than one that's been clean tilled on top. In this case, we've got straw that's been evenly incorporated in contrast to straw that's been rolled over, say with a moldboard plow. Now in real life, a moldboard plow doesn't make it horizontal like this. It puts it at an angle. Nevertheless, straw improves water penetration, right? Well, it depends. If the straw is evenly mixed in with the soil, now we've got a bunch of macro pores in the straw, then yes, you can see that this layer of water here has made the wetting front go down deeper than here where there's no wetting front. But what if the straw is not evenly mixed in the soil and we just have a layer right there? Well, now we've got a similar situation to what the sand was, and the water won't naturally go under here unless the soil gets saturated at that point. In addition, which one of these two crop residues is going to break down quicker? Well, it's going to be this one by a lot, because this one has the surface area for the microbes to work on, and it's also got the moisture for them to live in, while this one has neither one of those things. Coming down then a flood irrigated field. The water is across the entire thing. Water soluble dye, you can see which way it moves. Notice which way these salts or fertilizer, depending on what we're talking about, is moving. Basically straight down. If we switch this to a furrow irrigated field, we've got kind of an interesting pattern. In this case, the water is in both of the rows. And if you look at where, hypothetically, this is nitrogen fertilizer in the furrow, and your crop is here in the row, how much of this nitrate fertilizer would be used by the crop? Probably none. I bet it's getting flushed out before it gets up to where it's at. In fact, we'll jump ahead a little bit in time so you can see that. There's really no practical way for it to get in here. Where would be the most agronomically efficient place to add nitrogen fertilizer to this? And it'll be side dress with a shank in between the wet row and your plant. because you can see how that just moves sideways straight to where the crop is. Flip side argument though, let's say that this is a crop of dry beans, very, very salt sensitive. You're furrow irrigating. In this case, where is the salt being concentrated? Right where the middle of the dry beans are. How do you stop this from becoming a problem? You irrigate every other row, or you have 2 rows of beans between your wet rows is what I most typically see. Then the salts get concentrated in between the 2 wet rows, which is not where your plants are centered at. This is applicable for surface irrigation, especially something like potatoes or sugar beets or onions, something where we actually build a row. In this case, we've got a nice even slope, and the water in this case is not put in the furrows. This is being applied to the soil with overhead irrigation. There's also some plant material here, crop residue on top to give us a good soil condition. Notice how the wetting front mirrors the shape of the row on top. If you make that row more steep, look what it looks like. What's happening here is extremely localized water runoff. Water is hitting the row, moving down slightly, and then sinking in. Way too much water here, not enough water to where our crop actually is. For this reason, my favorite shape of row is as flat as you can put it on top. We don't want a steep row if our purpose is to increase water penetration. In, say, raising potatoes in Michigan, where one of our agronomists goes to, they deliberately make their potato rows really tall and really steep. Why? So when they get a 3-inch rain out of nowhere, that extra water goes through here, and the potatoes, which are very water sensitive, stay up where they're high and dry. So that shape of row can be very important for how the penetration works. Questions on that stuff or comments on it? Now, one side topic, not side topic, directly relating to this. This is some more grid sampled fields that I work on personally. This is a very good farmer who does a great job with soil amendments, elemental sulfur, sulfuric acid, things that we're going to talk about tomorrow, gypsum. This is a map of the sodium level in his fields. The blue is above 5%, the green is less than 3%. So blue is a problem in this. I point this out because the pattern you're about to see, I literally see in over half of the fields that I work on, that we do the grid sampling on. Notice that this is a half pivot, is his form of irrigation system, and he uses solid sets in the corners. Guess what kind of irrigation system is on this field? It's a pivot right here. Can you see it? This is a pivot. This is a wheel line. These are solid sets here in these 2 corners. How about this field? What kind of irrigation system? Yeah, pivot. Now the inner spans of a pivot tend to over irrigate. They have to nozzle them that way so they don't get plugged up too much. Can you see the inner spans of the pivot? This is my favorite one. First of all, 2 ones. This is sodium on this side. This is soluble salts. White is less than 2, so it's good soluble salt levels. The darker cyan is greater than 3, which is high enough to start reducing the yield of potatoes. What kind of irrigation system is on this field? Pivot right here, wheel lines right here, and he knocks off one of the wheel lines as they move the wheel lines up over here, is in that corner. So what's going on here? Numbers from his farm. Under the center pivot, one rev was putting on 0.8 of an inch of water. If we assume 90% efficiency, and it's probably not that good, that's 0.72 inches of water is hitting the soil. Assuming we do a perfect job of irrigating potatoes, which is waiting until they're 35% depleted of available water, that means that one irrigation of the pivot will push the water down 0.6 feet, 7 to 8 inches. If we look at the solid set or wheel line portion of his field, 64-inch nozzles at 60 pounds, 11-hour sets, we're putting on 2.2 inches of water, which is going down 1.8 feet. On average, the pivot's going around 3 times for every solid set or wheel line irrigation. On average, both of these fields are getting the same amount of water and the right amount of water for potatoes. But where are the salts being accumulated? In the pivot, they're accumulating 7 or 8 inches down. In the wheel lines or solid set, they're accumulating 2 feet now. So how do we fix this? Once again, this is a good farmer. This is not a guy who's pinching pennies and not putting everything on. This is a good farmer. Oh, and I was going to mention, his fields are naturally well drained. He does not have a high water table. The water table is greater than 150 feet on all these fields going down. So this is not a drainage issue. How do we fix this? The answer, yeah.
So deeper irrigation with less frequency.
One thing he did is slow down the pivot. So instead of going at 8/10 of an inch, he's going at about 1.2 inches. So that's pushing it down to 10 inches instead of 8, which is better. But he can't go any slower than that without getting excessive runoff. So what does he have to do? He needs to deliberately, on the pivots only, irrigate when the crop is not growing in order to leach out those extra salts and sodium. It was mentioned earlier, what happens if you add the calcium and elemental sulfur to free the sodium, but you don't put on the extra water, it just stays there. That's what's happening right here. It's just staying because the extra water isn't going on. In these solid set or wheel lines, he's naturally getting enough leaching. If you've got furrow or flood irrigation, you naturally get enough leaching. But as you shift to a more efficient irrigation system, like a center pivot, or even more so drip, you lose that I naturally get leaching without meaning to. The good thing about this is you get to decide when to do the leaching. So we don't have issues with nitrogen getting washed down as much. The bad side is you have to deliberately do that or else you'll get a buildup of salts and sodium in the pivot areas. Yes.
Does that mean the pivot never gets to field capacity?
Is the question, does that mean the pivot never gets field capacity? Actually, the math on this assumes that you're going from field capacity, from depletion up to field capacity. And what's happening is the pivot never gets saturated. So we never get that deep penetration past the rooting zone of the crop that way. Right. So realistically, what it means is in the fall, when nothing's growing, because yeah, this pivot doesn't have the capacity to put on more water than the crop's using in late June, all of July, and the first part of August. You know, we probably have an evapotranspiration of 0.4 inches per day, and this pivot's engineered to put on 0.3, 0.35 inches per day, something like that. So even if he runs it as slow as he can go without leaching the entire June, July, and August, he can't get it. So he needs to do this in the fall or early in the spring when the crop is not using the water to deliberately leach out those extra salts. Yes.
And just to finish my answer, I guess, sorry, the other thing I recommend that we have really good success with is to use a tillage implement called a no-till subsoiler, which lifts and fractures the soil. And that brings our infiltration rates from a pivot up to 9 inches per month. And we can, so that changes the physical characteristics of infiltration with different tillage, which does not destroy organic matter. So,
Yeah,
so that's been real helpful for it.
Yeah, so because the most he can go is 1.2 inches per rev without getting runoff.
Right.
So better water infiltration ability would allow you to force it deeper when it does that. Yes, Chris.
So how much should we put on? I mean, what's the amount? Is it 2 inches? Is it 3 inches? Is it 1 inch to get that pushed down there?
I would say you don't want to put on more than 2 inches because the water's already going down 1.8 feet. One thing that's been well noted, you can raise a crop with less water, with less nitrogen fertilizer on a pivot than on wheel lines, and less on wheel lines than on gravity. Gravity sugar beets are going to take probably 40 units more nitrogen than sugar beets under wheel lines, for example. Why? Because of this extra leaching that we're getting, that we're losing some more of the nitrogen that way, which is actually what I'm supposed to be talking about right now, and I will jump into at some point. But yeah, there's a balance there. There are actually places in Idaho where they have torn out pivots and put wheel lines back in because they have difficulty getting enough leaching with the pivots. And we're dealing with, say, salty waters and saline alkali soils. That's not what you want to do from either a financial or a labor standpoint, but it's been done because of that. Yes.
This is beautiful, what you're showing here, grid sampling under a pivot. I've never seen that, and I really appreciate you taking this dog leg. I think it's fantastic.
You're welcome. Honestly, this is absolutely common. No exaggeration, 60% or so of all the grid sampled fields that I look at in Idaho, you can tell exactly where the pivot is. just because of the salt and sodium accumulation.